So I know that the stuff that I'm going through here is there's a lot to it. I want to say that this afternoon what we're going to do is go through a real driver, developing a real driver from a very simple one that's like less than 100 lines of code, and then working our way up to more complexity so you can see how that it isn't as overwhelming as this, I guess is what I'm trying to say. So another thing that has to do with the standard EPICS device support is where does an output record, for example, an analog out or a long out, get its initial value when your IOC boots? And it's good to understand this. So, the first place that it can get it is from the DBD file. Usually the values in a DBD file are 0, right? It can get it from a database file that you load, right? So in your database file, you can say that the val field is 6. In asyn device support, the init record function, which is the function that's called in device support once for every record, attempts to do a read from your driver to get the current value. So the idea here is to support what are called bumpless reboots, so that when you reboot the IOC, your output records reflect the current state of the hardware. So if your driver returns asyn success, which is 0, on that read, then that value is used. So you should write your driver so that if you believe you have a valid value from the hardware when your driver initializes, you should set it so that it will return asyn success on a read operation. If you don't think you have a valid value from the hardware, then you should return an error. Then it won't attempt to use the value that it read from your driver. This means if you're using asyn port driver that we're going to discuss next, then if your driver has set that value in the parameter library with set integer param or set double param before init record, i.e. typically in the constructor, then these read functions will return success. If you have not called set integer param, they will return the base class will return an error. So a good way to do this with asyn port driver is if you have a good value, set it in the parameter library. If you don't set it in the parameter library. And for string out and output waveform records, then this readback is only done if the asyn tag initial readback is 1. Typically, for a string out record, which is a string you're writing, you don't want to read that from the device, because typically what you read from the device is not what you would write to the device, right? For register kind of devices, it would be, but not for strings. So typically that's not set to 1. And then, so this is the order in which things happen. So if this failed, it would be using the database file. But then the next thing that happens is save restore. So if save restore autosave is auto restore is running, then even if you put a value in your database file, that will get replaced by the value that's in save restore. And then finally, at the end of your startup script, you might have a dbpf, a db put field command to manually write a value to that field, to that record. So anyway, that's how when your IOC boots, this is the sequence of operations, if you're using asyn, that it will go through that determines what's finally the initial value of your output record. There's another, there's support in the generic asyn device support in relatively recent versions of asyn to do callbacks, not just for input records, but for output records. So normally output records wouldn't use callbacks, but sometimes you want a driver, if a driver does a callback with a new value, you would actually like not just your input record to update, but your output record to update to have that be the new value of the field. You can enable that with this info tag, asyn::readback1. And an example, if you guys have used Area Detector, you know that there's a file number field for all of the file plugins. So it can make each file have a new number. And this is the definition of that in the Area Detector database. So it's a long out record with this asyn link, and it has asyn : readback 1. And what that does, that means that when the driver is saving files, it's updating that that parameter, the file number, and doing a callback, which will update the readback, the RBV field for that, but it will also update this so that the output record is now in sync, and it knows that that the last file that was saved was file number 51, and so you can either write to it you could reset that number or change it here, or the driver updates it. So it keeps the two in sync. So there are cases where this is useful. There's a record that is used a lot in Synapse and in Area Detector. That's called a busy record. For those of you who don't know about it, the busy record is essentially exactly the same as the BO record, the binary output record in EPICS base, with one difference. It doesn't call rec global forward link, in other words, to process the next record in the chain until the value goes to 0. Only on a 1 to 0 transition does it call rec global forward link. The reason that that's important is it lets you do, with a channel access client, to do a CA put callback. And a CA put callback means, do a channel access put and then call me back when you're done. And the busy record, and that doesn't happen until rec global forward link is called, that the callback will occur. So that's a way of having your device, let's say a detector, the acquire PV, start, is a busy record. So you write 1, and it goes 1, and only when it goes back to 0 will your client get a callback saying this operation is complete. And the busy record implicitly has this asyn readback 1 in it. You don't have to do this. It's always done, because whenever the driver does a callback, you want the busy record to process. The important thing is that when the output records process due to this callback, they have to know that they're being processed due to a callback, so they don't write the value back to the driver again. When the record processes because of the callback, it needs to know, hey, this was a callback. I'm not going to call the driver again. Right? Anyway, so that's something to know about. And the busy record is really important to know about, because that's how, like, for instance, the EPICS scan record is all based upon this CA put callback. That's how it knows when your positioner is done. The motor record doesn't call rec global forward link until the record is completely done, until the motor is completely done moving. And the detectors don't call rec global forward link until acquisition is done. asyn comes with its own record. So there's an asyn record that provides access to almost all of the features of asyn, including the standard I/O interfaces. So this is what the MEDM screen for the asyn record looks like, and it lets you do things like turn debugging off and on. It lets you connect this record to a particular port and a particular address, and you can put in that string, the drivinfo string that comes at the end of the link. You could say what interface you'd like to communicate with this port on. So it lets you do a lot of debugging. It lets you do interactive I/O. So if this is connected to a TCP driver, for example, there's another field, another screen you can pull up here that lets you just type a string. All right? Send a string to your device and look at the response. It's a very useful thing to have when you get a new device. And the vendor says you're supposed to send this string and get this response. But it turns out when you send that string, you don't get that response. So you can do debugging with it very easily to learn how your device works. Yeah. And it can even be used in your database for real I/O. So you could, instead of using stream device, I've got databases where I just use ASIN records to send and receive strings, and then some, like the Synapse comes with an like an scalc out record, things that can parse the return strings. So this is, it's connected to a serial port, and I can type some commands here and get a response back from the device. So you can, this is where you would type what you want to send to the device, and here you can control, you can see what the device sent back to you. You can change the terminators, carriage return line feed. That's often what you need to play with is, what's the correct terminator. Also, what baud rate is this thing actually talking at? So you can, over here, you can change the baud rate, the data bits, stop bits, and so on. With GPIB, there aren't too many of those devices around anymore probably, but you can control the GPIB operations here. You can, with the same ASIN record, so this was the same ASIN record that here was connected, well, it might have been connected to a serial port. By typing in here IP330_1, I've connected this to my IP330 ADC driver, and now I can say I want to talk to that driver on the int32 interface, and I want to do a read operation. When I hit process, this is going to read my ADC. Right, so I'm actually communicating with my ADC. Yeah.
How one can get to the that behavior?
Oh, it's
yeah,
it was here was more that brought up.
And one of those. Okay.
Yeah, it's one of these mores brings that screen up. So. I by the same ASIN record that was previously connected to a serial port, I just reconnected it to a different port, and I could read the actual data from the ADC. The same ASIN one, I now hooked it to a digital to analog converter, to a DAC, and I said I want to use the float64 interface, and I wrote a value here. No, I'm sorry, this is the float64 interface, so I wrote 500. So I've changed my my device, so I'm writing a value to the DAC in this field. So it lets you do, lots of pretty useful debugging can be done, in your GUI instead of having to do it, by writing a C test program or a Python test program. All of the interfaces in ASIN also have a synchronous counterpart. So meaning, I showed you the way you had to do this. You had to call ASIN manager queue request, and then you actually did the I/O in a callback routine. That's how you have to do it when your driver, when your code is running somewhere where it is not allowed to block, like device support. But there are times that your code is running where it's okay to block. And when it's okay to block, an example is in EPICS device support, even in the init record, you're allowed to block. So when the IOC is booting, you're allowed to block. In a state notation language program, for instance, it's running in its own thread. It's okay to block. So what you want is a synchronous interface, so you don't have to worry about the complexity of calling queue request and a callback. You just want to say write. And so there's an ASIN octet sync IO write. You just call that, and you can directly write to your write or read from a driver. For instance, if you've got an ASIN port driver that has set the CAN block flag, but it needs to communicate with an underlying ASIN octet port driver, like the motor driver might be communicating. Your motor driver might be communicating via an underlying TCP or serial port driver. You're allowed to block there, so you call these sync IO routines. Or again, the MAR area detector driver talking to a Pilatus CAM server, which is a socket interface. It calls these sync IO routines because it's simpler. So here's just an example of a synchronous interface with a scope. So this was a VXI11 scope. So in initialization, it connects to the underlying VXI11 driver, and then in the I/O, it just calls octet sync I/O write read to this using this asyn user scope, which got connected to the device. So it can just synchronously do write read operations in the Tektronix scope driver. Okay, asyn provides a lot of commands that are available at the IOC shell. And I'm not going to go through all these, but the first one, asyn report, very important. You just say asyn report with no arguments. You'll get a brief list of the status of all the asyn port drivers in your IOC. If you say asyn report 10 ADC1, you'll get a report at level 10 of that particular asyn port driver. Which might tell you a lot. You write the report function, so you can say what it is you spit out when it does the report. This lets you turn debugging off and on, and I'm going to get to that in a minute. So all these asyn set trace commands let you turn on debugging at different levels in your driver. This would be to set asyn set option. That would be setting the serial port, baud rate, and so on. Show option. See if there are any of these. Oh, here the asyn set output and input EOS. So that's how you tell it. Your device sends you carriage return line feed, but you only want to send it carriage return, whatever. Okay, tracing and debugging. So this is a really nice part of asyn. So it has a standard mechanism for printing diagnostic messages in both device support and in drivers. The messages are written using the EPICS logging facility, or they can be sent to standard out or standard error or to a file. So in your driver or device support, you call asyn print. You pass it this pasyn user so it knows what driver and device this is from. And then this reason here is asyn trace error, asyn trace warning, asyn trace flow, and so on. So if you're printing an error message, this would be asyn trace error, and then you can give it a format string and a bunch of data. The user at runtime can enable and disable all of these types of messages. So by default, usually when asyn manager creates a port, asyn trace error is enabled, but all the others are disabled. But with your MEDM screen here, you can turn on debugging at all these other levels, and you can also do that at the IOC shell command, either one. You do it with the GUI. And then when you're, plug in, but I am plugged in. No, I'm not. I plugged in one end. No, I am plugged in. This must not have power.
On the right side.
Over here? Let's see if that one's working.
Yep.
Yeah, you saw it. It went away or something? Okay, good. Yeah. What was I saying? Oh, so then, and so the nice thing here is that you can turn on this trace debugging for a particular port and address. It's not like some global flag that says in this driver now all debugging is turned on, and it might only be one of your ports that needs debugging, and you don't want to see it from the other 20. So this is nice. You can turn it on for a particular port and even a particular address. You can turn them off and on, as I said, from the shell. You can also, if your driver calls asyn print IO, it passes it a buffer and a length, and then the user can select here how to print that buffer. So should it be printed in ASCII? Trace IO escape means print in ASCII, except unprintable characters are printed as backslash their octal equivalent. Excuse me, trace IO hex, so you can just see it in hex. And then you can say how much of the data do I want to see, because if it's a 50 kilobyte buffer, you don't want to see the whole thing probably. So you can set that. you can also say, what other information do I want to see? The time, what port it came from, and what line in the source code did it come from. You can turn those off and on. And then finally, you can set a trace file. So that's very useful if you don't, you want to save it, first of all. And also, when it goes to the console, that's often rate limiting. It slows things down, particularly in a VME or crate. Those are often like 9600 baud or something, right? So it really slows things down. So if you send it to a file, it's likely to change the performance. A lot of times when you turn on debugging, the error goes away, right? Because it's a race condition. So by sending it to a file, it makes it less likely that it's going to go away because it was a race condition. Okay, so ASIN includes a number of drivers in the module. It has a driver for a serial port. This works for serial ports on most operating systems, Linux, Windows, Darwin, VxWorks, RTEMS. So you call driv serial port configure, you give it an ASIN name, you give it the name of the device on your system, and then you call this ASIN set option to set things like the baud rate and the parity and the stop bits and so on. The TCP driver, so you give it a port name, you give it host info, and all of these drivers have a priority and auto connect and process EOS. These are no auto connect and no process EOS, so that if you put 00, the default is that it will auto connect and it will process EOS. And the host info here is the internet host name, port number, an optional local port number, optional IP protocol. So it's host, port, local port, protocol. And the protocols that are TCP, which is the default, UDP, UDP broadcast, HTTP, which is like TCP, but the server closes the connection on each transaction. So this reestablishes the connection on each transaction. And then COM is used for like Moxa boxes, terminal servers, which use this Telnet RFC 2217 protocol. So it lets you set the parity and baud rate on a remote device on the Moxa box. So you don't have to just set it up with the GUI.
Is there a meaning to the upper capital UDP versus capital TCP?
No, that's case insensitive.
That's insensitive.
Yeah.
What is that? I've never seen serial 8 and 3, for example. Is that IP?
This would probably be the name of a Moxa box.
Oh, okay.
A IP name of a Moxa box.
Name.
Yep, host name. Yeah, so you can use host names or host numbers. It does that. There's also an IP server port, so you can create not a TCP IP client, but rather a TCP IP server. So it's listening on a socket driver listening, and it would then connect to some other code that you've written whenever there's an incoming connection. VXI 11, that's like GPIB over Ethernet. There's GPIB drivers for VxWorks and Linux, and then there's a USB test and measurement class that works with some USB devices. So these are all the drivers that are in ASIN. Then, of course, there's a whole suite of drivers that use ASIN, but that are not part of the package, like area detector.
Is there anything for the multicast that you would specifically open the multicast?
I'd have to look at the documentation. I don't know if that's been supported. I've certainly never used it. Yeah. Okay, so I think this is the last slide. So advantages of ASIN. The drivers implement these standard interfaces that can be accessed from multiple record types or state programs or other drivers. This generic device support eliminates the need for separate device support in probably 99% of the cases. When we converted Synapse to ASIN, it reduced the number of lines of code in Synapse by 10 to 20%, but there were like 50% fewer files because a lot of this device support went away. you get this consistent trace debugging at a port address level, ASIN record for debugging and actual I/O. It's easy to add. If you have an existing driver, it's easy to convert it to ASIN. That's probably not such a factor here because you probably don't have a lot of legacy code. As I said, ASIN drivers are actually EPICS independent. You can use them in another control system. And what I'm going to talk about next is ASIN port driver that simplifies a lot of the stuff that I went through in this talk. So you can kind of forget some of the stuff that I told you in this talk, except that you should be aware that it exists. Right? Particularly if you want to improve ASIN port driver. Right? You know, if you want to enhance ASIN port driver, you need to know, because ASIN port driver is just a layer on top of the C interface to ASIN. So you need to understand the C interface to ASIN. Any questions?
Actually, for me, it seems that a lot of abstraction and possibility very flexible. If I have a concrete device like I have a camera, USB, with
Yeah.
motion possible, then how do I structure this ASIN driver? Do I use multiple port, multiple address, multiple interface? Because
Yeah, that's a good question. I mean, we'll get into a little bit of that this afternoon when we're dealing with a more concrete device. If the motion was multiple axes, for example, you know, you might implement that the the x-axis is address 0 and the y-axis is address 1 and the z-axis is address 2.
so one port. For
Yeah, just one port.
And then multiple addresses.
Yeah. And then, you know, one of the things that, if it's and you'll see this, well, with motor and area detector and quad EM, that there's a whole family of devices that are similar, right? But they might be quite different in how you actually talk to them. What is useful is to write, in that case, to write a base class that provides the abstraction for a quad electrometer or for a motor, and then derive from that base, and that implements the common features of that kind of device, and then derived classes that handle the specific features of your model of motor or your model of detector. And as you'll see tomorrow when we go through area detector, there's quite a few levels of abstraction there. So it starts with ASIN port driver that I'm going to talk about next. But then there's a class on top of that that's called ASIN ND array driver that implements the interface to an n-dimensional array. But it's not yet an area detector. So at that level, the quad electrometer derives from that. And the multi-channel analyzer can derive from that because they deal with n-dimensional arrays. Then on top of that, for the quad EM, there's a base class, and for the area detector, there's a base class. So, you know, we end up with a hierarchy that's maybe a half a dozen classes deep. And each of those base classes handles the common features. And then the derived classes, the specific ones. So if your camera fits into area detector, you could derive your driver from that, right? And a lot of the stuff would already be done for you.
But let's say if we have the device, is there like a table that we say, okay, let's go to Tektronix, and because it's similar, is there some kind of a mapping that we could just go and basically steal existing code and say, well, this is so similar to this?
Yeah.
Because it's got, let's say, IP interface, it's got this.
Right.
And we just modify it, and it's much easier to kind of...
Yeah. I mean, there is that for certain things. Like, and the guys at Slack just adopted, they liked the way that area detector did that, right? So they did the same thing for transient digitizers, right? They made a base class that should handle all transient digitizers, and then they did derived classes for the particular models that they had. That should be done for oscilloscopes as well. There was one project for doing oscilloscopes, but it isn't based on ASIN port driver, right? It preceded that. So, you know, it's something that you could refactor, right? So that it now, you know, uses these features, which would probably make it simpler. Any other questions? Okay.